All right, it's time. Any questions from the homework? Nick?
3.5, number 3.
3.5, number 3. Number 3. All right. Okay, so what we have here is a product rule for both sides, implicit differentiation. So for the left, for the right, y prime, y prime, y prime. So one, two, three. Oh, finally. I would say that will be the answer I got for this long process. So I think the key is just recognize it's a product rule. And yeah. Looks okay. All right, Emma.
Can you do 3.421?
All right, this one is again playing with the symbols. So I would say get used to the symbols first before you plug in any numbers. Okay. F, G. Okay, and all right. First job, find f prime 6. Okay. F prime x is going to be fx prime. So before this was a g, right? It's easier to differentiate between f and g, but now you just have to be careful whenever you put a G, put an F instead. Sounds good. Okay, now this part is this 4. F6 is going to be 3. F prime 3 is going to be 9. So the whole thing becomes 9 times 4, which is 36 for question 1. Now for question 2, you want G prime 6. Square prime, which is first handle the square to the 1 times F prime X. So F prime 6, we just did it. It's 36. Okay. F6 is going to be F6 because F is FF. And F6 is 3. And F3 is 2. Sounds good. All right. Aaron?
3.4, number 27.
Ho, ho, ho. Again, for a problem like this, you know the ln3 there is just try to confuse you. Okay, it's confusing. Then how about we change it to something nice? We change it to be 2 to the x to the 12. How do you handle that? Well, clearly I have to do this. Then I need to do the derivative of x plus 12. In this case, it's just 1. If I do that thing for 2, I just need to do that same thing for ln3. Don't change a thing. And then times the ln of that thing. Looks all right? Cool. Other questions from the homework? All right. We were talking about exponential growth. Then we talk about, okay, number 1. This is the differential equation. The solution is exponential growth. That's beautiful. We set up a very simple equation. Okay. We end up with having the whole principles behind the idea why this one is exponential. It's because your changing rate is proportional to your current size. Compound interest works this way. Radioactive decay works this way. Okay. Now what about y prime equals this, which is more realistic because we have limited resource. Say the environment can only take 5,000 population. Then the whole thing changed to logistic. 5,000 is the bar. And you become something like that. Okay. Now we can say, basically we have the freedom to set up things to be anything. For example, we can set up everything like this. Then we just add one more thing, that is how we are going to harvest the fish, if it's the fish, or how we are going to actually cure the cancer by killing some of the cells at any time using a drug or something like that. This become a control problem. That is, I know your differential equation, and I know your solution, and I don't like your solution. So I want to do something to the equation in order to get the solution I want. Sounds good? That's kind of like harvesting the fish without hurting the environment. That is like, well, if you got too many, let's say, I don't quite remember, deer or moose in Yellowstone, we actually add in 20 wolves from Canada in order to actually retain the balance back. Okay, how do I do that? I basically manually interfere with the differential equation to change it to another differential equation. Okay, but in this way, the solution becomes the one I want. So it's called the control problem. You can use that thing to cure cancer. You can use that thing to do SpaceX, because if you have a rocket, you basically control it to make sure that's going to land in the place you want to land and in the way you want it to be landing, with bottom down and head up. Self-driving car is another example. Roomba is another example. Okay, so anything involving robotics is basically control problem. If you're interested, check my website. The student, one student of mine actually built a self-driving car last year. Okay, originally I was trying to build a self-driving car going on campus, and then I was ready to actually pay $500 to buy a trash car and then modify it. And I was smart enough to call the campus police and say, hey, am I allowed to do this? And they said, no, definitely not. Okay, so I couldn't do that. It's not safe. And the insurance company won't cover it either. So instead, we built an RC car, which is roughly the size of this bottle. Okay, and that thing runs on the basement floor of the wings, which is a compromise, but still, it's pretty cool. And Roomba, in the last section, we raised a really interesting problem. So if you see Roomba is doing something stupid, right? Will you feel sympathy for Roomba, for that small cylindrical body? Okay. What if it screams every time it hits the wall? Okay. Or what if you go there and want to turn it off? It just says it was programmed to do so, by the way. Okay, just say, please don't turn me off. Or whenever you hit the Roomba, it just says, please don't hurt me. Okay, even though you know that it's programmed, will you feel sympathy for that stupid cylindrical plastic? I don't know, whatever, how to call that. It's basically a piece of plastic. Okay, that's an interesting thing for you to think about. And where is the moral of treating robots? Since when, starting from which point you would think, robots start to become a human and they should deserve some basic rights? Okay. Another thing people actually did study was really interesting. That is like, you will feel sympathy for anything that has a face. So if I just give you a rock, I just draw two circles there representing the eyes, and then one small, I would say, a circle or like an ellipse, or maybe even just like a slash flat line to represent the mouse. Suddenly you will feel like, wow, that is a lovely rock. Like, yeah, it's a friendly rock. You know, so it's really interesting to see how human brain works. But that's some side topic. All right. Then we'll promise you that we're going to introduce the harmonic oscillator. By the way, this one has a very cool application, which I can show you later. Harmonic oscillator, which is basically a spring mass system. We have something attached to the wall, relaxed at 0. What I do is I pull this thing away from the wall to here, so I feel tension from the spring. I release it, and I assume there's no friction. Then what's going to happen is this one is going to start from here and then shake all the way to here. Then there's no force anymore. But then this one is going to keep shaking because that still have a velocity. And then it shakes back, it shakes back, it shakes back, it shakes back. And if there's no friction, there's no loss of energy. This one shakes back and forth forever. Sounds good? Okay, that's what we observe. It's roughly a sine or cosine curve. Now, of course, we're investigating y. Just like the way we investigate why the population is exponential growth. Turns out there was a differential equation nothing satisfies. For this one, we can do the same thing. All right. Let's take y, which is a function of t, to represent the distance from the relaxed point, basically 0. So you can see this y change as time goes by. Okay, it can be negative sometimes. That means it goes to the left of the relaxation point. So positive, negative, positive, negative. Y prime t, what is the changing rate of the distance? Velocity. And what is y prime prime t? Acceleration. I don't know how to set up an equation with the distance, but I do know how to set up an equation with acceleration, right? That's F equals ma. Everybody knows that. That's Newton's second law. Then I can put my y prime prime here, which means I am half done. I have a differential equation which involves the second derivative of y. Sounds good? Now I just need the force. Do you know how to calculate the force from a spring? Something called the Hooke's law. By the way, you need to pronounce really carefully. I call this one Hooker's law for 3 years. The first time I was teaching at Auburn. Every time I teach, people just laugh. I don't know why. I feel offended. It turns out I was the one who was doing that. Hooke's law. Have you seen something like that before? Okay, roughly it tells you this. If you have a spring, the more you stretch it, the bigger the force. Okay, the more you compress it, the bigger the force. That's number one. Number two, how big is the proportion really depends on how strong your spring is. For a very strong spring, you just stretch it for 1 centimeter, it's going to be a big force. But for a really relaxed spring, a weak spring, 1 centimeter probably doesn't mean that much. Sounds good? Finally, why negative? Well, think about it. If you stretch the spring to the right, where does the force, which direction is the force going? To the left, because it's trying to resist where you're going. Okay. If you compress the spring to the left, what's the direction of the force? It's going to actually push to the right. So that's why we have a negative sign here. Sounds good? With that in mind, let's just put negative k. Of course, we don't have x. We have y in this case, which represent how much this one is stretched or compressed. That's it. That's the differential equation for spring mass system, where m and k represent the mass, and k represent the spring constant. Bigger k means stronger spring. Sounds good. Can you solve it? Well, let's first move this one to the other side. This together is a constant. All right. Do you know some function that if you take the derivative for twice, it basically becomes itself with a negative sign? Which trig? You have 6. Anton?
I want to say sine, but I'm not 100% sure.
Why don't we just try it? What's the derivative of sine?
Cosine. Oh, yeah,
What's-
and then negative sine. Yeah.
Okay, here we go. So what did you do? You take this one, you take the derivative for twice, it's then become itself with a negative sign. Okay, so this one solves y prime prime equals negative y, which means there's a 1 here. Sounds good? Now we want a special constant. We want k over m. So how do you modify this? That's definitely a sine, for sure, but modified. What's the derivative of sine 2x? 2 cosine 2x. Sounds good. What's the derivative of this one again? That's going to be 2 coming from the first 2, and then I produce another 2 coming from the second derivative. Good so far? That means if I put a number here, I do the derivative for twice, then I'm going to receive this number squared. Because every time I take the derivative by chain rule, that number should come out multiplied. I do it for twice, I multiply that thing for twice. And the final number is this. So I think it makes sense for me to do that. You do it for once, you got square root of k over m. You do it for another time, you got another square root of k over m. You got two of them, k over m. Sounds good? Okay, so let's take an alien from outside. They never played with spring mass before, not like you and us. We know that thing is going to shake. They just say, this is the first time I see a spring mass. Okay. But if they just write down this, they will be able to do the following several things. Number one, they will predict this one is going to oscillate. Without even have seen it in real life. They know it has to be this way because the equation told you so. Sine, cosine. That's great. Second, what if I take some oscillation of your spring mass system? I increase K, which means I replace it with a stronger spring. What's going to happen? Well, this number is going to increase, right? If you keep the mass and increase K, this number increase. What's the difference between sine 2t and suddenly you increase the number to sine 3t? You increase that number, what happened? Aaron?
The amplitude increases.
Where is the amplitude? The amplitude should be here. So not the amplitude,
The period,
actually.
period changes.
Yeah, bigger or smaller?
Smaller.
The period becomes smaller, which means you oscillate more frequently, right?
Yes, yes.
All right. So if you increase K, you actually become this. That means actually changing it to be a stronger spring doesn't actually change the amplitude. It changes the frequency. Meanwhile, if you decrease your M, which means you have the same as strong spring, but you make it a smaller mass, also you increase the frequency. That's going to be awesome. You can predict a lot of things, right? Number three, if you double the spring strength and meanwhile you double M, what happened? Nothing changes because K over M still stay the same. Okay, that's not so intuitive anymore. Can you see that? Okay, so that's why it's beautiful. Once you can solve it in a differential equation, everything becomes exact accurate. All right. Everything makes sense so far? Of course. Again, this is not the real case. Why? Because we assumed no friction. In real life, this never happened. You will always have friction. So what if you have a friction? Now ask your intuition. You may have different answers because, yeah, right? You just go by your intuition. Anything can happen. But now if you really think about it, it's just this. Spring. We just add another term, which is the friction. Still okay? And you can test that. People have tested. It's basically minus b times the y prime. What does it mean? Number one, it's to the opposite direction of your traveling. If you're traveling to the right, your friction goes to the left. That's why this negative sign. Number two, there is a constant to tell you how strong or how small that thing is. That's basically have something to do with the texture of the surface. You can have very small friction constant if you are basically sliding on oil or water. You can have really big friction constant if you have something on the concrete ground, for example, or on sand. Number three, it is proportional to how fast you are traveling. Okay, we can test this. That means if you are, I don't know, if you're traveling really fast, the friction is going to be really strong. Okay, and on the contrary, if you're traveling slow, the friction is just small. That matches common sense, right? For example, like if you're just running, and then suddenly you just stop and use the friction from the bottom of your shoes to stop yourself. Okay, will you be more scared if you're just walking and then stop like that, or would you be scared if you're just, I would say, how to say, you're actually running as fast as a car, and then you want to stop yourself by, using the friction at the bottom of your shoes to slow down? It's gonna be scary because your speed is so fast. Okay, you may actually, you may need to buy new shoes if you do that. All right, that's it. Nice, easy differential equation. Of course, solving it won't be so easy anymore. But again, setting it up is pretty easy. Anybody can set it up. How to solve it? Let's leave it to Wolfram. Let's leave it to computer engineers or mathematicians. Sounds good. That's the beauty of differential equation. You can handle anything you want. Now, if I change it by moving every term to the other side, basically what we have is just a simple second order differential equation that captures everything about a damped harmonic oscillator. Damped means you have friction. So eventually your harmonic oscillator should stop because friction absorbs your energy. You can even add more, okay? You can actually have some wave going there to try to induce that thing to shake or something like that. But we will talk about that thing later if we have time. Everything makes sense so far? All right. Now what I'm going to do is I'm going to take a completely new problem and we're going to solve it. If you can follow, you follow. If you cannot follow, just accept what I just said. Some of the rules you can Google it online, which is about electrical circuits. Okay. There is one basic law about electrical circuits. That is whenever you have electrical circuits, okay, the total voltage should equal to 0. That means you don't have any potentials there. Okay, gradually the whole potential just reduced to 0 in order to have a closed circuit. Sounds good? All right. Now you may have a lot of gadgets in this electrical circuit, but nonetheless, there are only 3 categories. Okay, if you have multiple of one category, you can put them all together and consider them all together. Okay, they are called the resistor, okay, capacitor, and inductor. Inductor here, capacitor here, and the resistor here. And each one of them produce some voltage with a different formula. For resistor, it's R times I. This is by Ohm's law. R stands for resistance. I stands for current. You have the capacitor, which is Q over C. Q stands for the charge on both sides of the capacitor, and C stands for the capacity, which means the capacitor is wider or narrower. Okay, how big the cross-sectional area is. Finally, you have the inductor. The inductor only produces voltage if you have a changing current. In another way, the voltage was induced by the change, okay, of your current according to some magnetic field. So L is just a constant for the inductor, and I, you know what I is. Maybe you know this before, maybe you don't know this before. It really doesn't matter. Okay, but the key is if the total voltage is 0, we can take the sum of these three things and make it 0. That will be the differential equation of an electrical circuit. Sounds good? Moreover, which is very important, I, which is the current, actually equals the changing rate of the charge. That's the definition of current. Sounds good? Now let's put it in. Whenever you see an I, you replace it by Q prime. You take a Q prime, you take another derivative, that's just Q prime prime. Rearrange the order, you have something like this. That will be the final differential equation the electrical circuits has to satisfy. Sounds good? This is the harmonic oscillator coming from a spring mass system. They may have different names or constants. But really, what you have here is just something double derivative, something first derivative, something original, times a constant. It's just like, do you want to call the constant L or M? Do you want to call the constant R or B? Or do you want to call the constant K or 1 over C? Still okay? Can you see these two equations are actually exactly the same? With just different names. That's a really interesting takeaway. In which universe will you think a spring mass system is the same as an electrical circuit? But now they do. They are the same. Sounds good? Okay. What's the application? The application becomes super interesting. Whenever you want to study spring mass system, you can actually instead study the electrical circuit problem and vice versa. Okay. So let's say you're trying to build an airplane. You know, when your airplane travels at a certain speed, which is, for example, close to the speed of the sound in the air, it starts to have a resonance with the air, the molecules in the air. Still okay? This is called sound barrier. It's very dangerous for the airplane. The airplane is going to fall apart because the vibration becomes so big. Vibration is nothing but harmonic oscillator. So vibration is actually a spring mass system. Sounds good? So instead of building the airplane, what you can do is you can actually just set up the differential equation. Do the control problem we just said, and say, hey, if I did this modification, this will reduce or stabilize the vibration of the airplane when it reaches the sound of the speed of the sound. Sounds good? That's step one. Beautiful. But then, of course, in order to verify your theory, you have to build that airplane. Take it with your design, push it to the speed of the sound, and see if that thing breaks. Sounds good? How confident are you to go to the military force and say, hey, I have a formula, I think I can solve that problem. Can you just lend me $10 million, let me build one game plane and just let it run so I can see if my method is great or not? Who is willing to do that? Raise your hand. You don't want to do that, right? So what do you do instead? You say, hey, you know, the airplane and the electrical circuits share the same differential equations, right? So if my method is going to work for the airplane, equivalently, it should work on the electrical circuits, right? So instead of testing the whole airplane, what you can test is actually you can just build an electrical circuit. Set up all the coefficients to be exactly the same in the airplane and see that electrical circuit breaks. Sounds good? How much is that? $40. Okay. Do you see the beauty of this? How much money, how much trouble can you save? But how can you make sure that if this thing works on the electrical circuits, then that thing is going to work on the spaceship? And the answer is because mathematically they're equivalent. Sounds good? That's the beauty of abstraction. That's why you can say I can understand compound interest in terms of radioactive decay. Why? Because their mathematical equations are the same. Does that make sense here? That's the whole point of learning mathematics. You're trying to do something abstract. Do you guys realize that? Have you guys realized that before? Okay. How do you count apple? 1 apple, 2 apples, 3 apples. How do you count pig? 1 pig, 2 pigs, 3 pigs. How do you count people? 1 person, 2 persons, 3 persons. Do you feel offended if I count you the same way I count pigs? Do you feel offended? Not really, because you know the point is not about pig, people, or apple. It's about the thing in common. It's about the symbol. It's about the abstract thing. Sounds good? What's the beauty of this? Well, let's say you're a farmer. You want to count how many apples you have. You go to for example, I don't know, go to a college, maybe not college, go to a center. You study for 2 weeks, you get a certificate how to count apples. Okay, finally you come back, you're ready to count the apples. Turns out apple season is done. Now you want to count orange. What do? You go back to the center and get another certificate on how to count oranges. You come back and then you go there, you get another certificate on how to count cows. Until you realize, how about I just take a college degree and say how to count, regardless of apple, cows, or actually they don't really matter. Make sense here? Okay, so the key of learning mathematics, you may lose it as you go, just like this thing is not useful. It's not in real life at all. I mean, have you seen one before? Personally? How big is it? Is it soft? What's the smell? What's the color of one? Have you thought about this thing actually does not exist in real life at all? So the connection is actually when you put meanings to this, that's when you have a model. But this thing actually happens purely in your head. That's the reason you're taking a mathematical class. You're trying to train your head. Is it useful? Yes, because when you go to a real world, you just need to project that thing to the real world. The harder part, it has been done already in that class. Okay. But the way we teach it, of course, we manipulate the symbols without telling you why. It's very easy to get lost in the mathematical symbols and say, hey, this has nothing to do with real life. Actually, it's wrong. Everything has something to do with real life. Okay. Sadly, we cannot teach that as we go because there are already, enough math content to cover. This is beautiful. This is really beautiful. Okay. So think about, for example, you're building a car. You want the car to have a really nice system to absorb all the vibrations from the road. Do you really want to build the car, or actually do you want to build an electrical circuit? For the first round, you can actually build 200 electric circuits. Feel free to break every single one of them until you find several ones which will work. Then you use that to design the car and test the car. That's how this works. All right. That's pretty much it. I introduced the 2 systems, and the second system of spring mass can also work on electrical circuits. That's already actually a lot of modelings. Okay, it's very useful already. Of course, there are many other more differential equations. And you can also build something on your own. For example, think about free diving. Okay, you have an airplane. You just jump out of it. That's you with a parachute. Okay, well, how do you model that? Number 1, let's not talk about free diving. Let's talk about free fall. That means you jump out of it without without the parachute. What's going to happen? Number 1, a tragedy. Okay. Number 2 is it's pretty easy. It's mg That's my force equals ma. Sounds good? That's free fall. Okay. So what will happen if you have the parachute compared to a free fall? Well, technically, we always say we neglect the air resistance. Why? Because it's so small compared to the gravity, right? Not the case anymore if you have a parachute. So what you have instead is this. Gravity. But now you have a parachute. You can experiment with it. The thing looks like this. It's proportional to your current velocity. This comes from the parachute. Now, what do you mean by designing different kind of parachutes? You're trying to change this K. Okay. How do you want to design it? Well, you have a target. The target is when you hit the ground, you want your speed to be less than 5 meters per second or some threshold. Otherwise, you break your legs, right? Okay. No parachute, you're going to hit it with a 50. You're definitely going to die. Okay, so what are you going to do? You're going to add this thing by changing the parachute in order to control the solution of a differential equation. This becomes a control problem again. And the thing you can control here is actually the parachute. Sounds good? Okay, so actually you can design all kinds of control problems by yourself. They are not even hard. We only covered the basic here, but I think it's already, how to say, useful enough. Okay, I can go on and give you more examples, but I think I will stop here unless you guys have any questions. So there's nothing to cover in terms of web work or exams for this section, purely just, discussions. Do you guys want to know is there anything that you guys want to know more about how to, anything related to this section or differential equation or control problems or, calculus in general? Do you find it interesting? That's the cool part. Okay. Anton.
I get that like K just like the value of K is referenced to various types of parachutes, but what would that like look like in real life?
What do you mean by look like? It's like how do you design different type of parachutes?
Yeah, like what does K really mean other than it varies the type of parachute?
I would say in a different way. That is, K is the constant, proportional constant ratio that you have with respect to your velocity square. Okay, so for different parachute, they have different K. All you need to do is actually use some design of the parachute, and then you test it and try to figure out the particular K for that parachute.
Oh, okay.
Once you have that K, you put that K into this equation to calculate if it's going to be safe.
Got it.
Then if the K works, you can basically say the parachute will work. Think about this, right? How do you test the parachute? You're not going to give it to 100 people and say, hey, you guys go and dive. And then you recognize, okay, 70 died, 30 survived. Great, let's make an adjustment. You're not going to do that, right? So what you will really do is just, you just put it into the equation. And you need to really trust the equation. And so far, it hasn't failed us. Okay, so that's basically how the procedure works. Now, second question, how to make a bigger K? It's very easy. Just make the parachute bigger. Okay, but then you have a problem if you make that thing bigger. Number one, what if there is a strong wind? Yeah, that thing actually save you from vertically. You may create trouble horizontally, right? It's like you're sliding really fast horizontally. That's one possibility. A second one is actually, even though two parachute design have the same K, can you somehow be clever about the shape and the materials in order to save money? Let's say K is, if you want to be safe, K has to be 20. And 20, if you just build a plain spherical parachute, it's going to cost you $400. Sounds good? Now, is there a way to add some plastic into it? Maybe adding some skeleton to it okay, in order to save the material and build the same K with only $50. So there's actually a problem after a problem. That is like, okay, this is the K we're looking for, but how can we be smart in order to save materials? Sounds good? Okay, so there's a lot of designs behind this. And actually, if other people can build the same K with $200, and if you can do it with 180, you'll make a tons of money. That's why a lot of companies are actually throwing a lot of money into research and development, because as soon as you have a better technology, okay, or better design, you do have a lot of money involved. Okay. Cool. Other questions? Even if you just think about building filters, like the filters for in the cups you drink, okay? Or maybe some, for some chemical reactions, except chemical filtering, which has to be really, really careful. How many layers of filters do you want to put here? Think about it. Do you want to put a single layer? Okay, with really small pores? Or do you want to do multiple layer? The bigger one actually got filtered out, and then the second level, the intermediate one, the third level, really small one? Or do you want to do a smaller one, and then a bigger one, and then a smaller one? Kind of makes sense here? By changing all the arrangement, every single layer you add cost. Okay. Also, depending on which way you're going to do it, maybe you have something really, really good, but that thing can only last for 2 months. While if you do things a little bit in a different way, that thing can last for 2 years. Okay. So there's a lot of designs into those kind of things, and the mathematics is everywhere. Differential equation is involved in this. Probability theory is also involved in this because you could never filter out 100% of what's there, unless it's super expensive, right? So basically, you just say, hey, 98% or maybe 97%. Is roughly the standard of FDA or something. You just stay with that. Okay, similar way is actually how to build a mask. Like you wear masks right now, right? Do you actually tear us apart and try to see how many different layers are there? What kind of materials are used there? Okay, and why one is better than the other? Okay, that's a lot of technologies involved. With better technology, you can basically build better things with the same material. And if you sell them for a slightly lower price, you make tons of money. Okay, of course, and self-driving car, whoever has the better model basically make all the money. Okay, Tesla is doing pretty hot right now for self-driving because they have such, such great amount of data they collected during the past few years. Okay, anybody who is building a self-driving algorithm now is using the data collected by Tesla. And that is fantastic. Meanwhile, they do have failure rates, and you do see people get killed by Tesla. So yeah, that's how this is done in real life. Other questions? All right. If you want to talk more, find me after class. We can start to talk more. If you want to know more differential equations, that would be the keywords you're looking for. And also control problems. We do offer this class here. We don't offer classes like control here. Okay, so for this one, I think you can start right away. You don't need that much math to do it. Okay. Similarly with this. Okay. So for a lot of you, if you're interested, you just go and Google and learn it by yourself. I don't think anybody's going to take this class unless you are like a, I don't know, physics major or a math major, but it's really not hard to learn. Okay, for the basics. If you go to this class, we teach you a lot of things which is not necessary. So I would recommend start to learn by your own. Give yourself 2 weeks intense study. You will understand this or this pretty well. Okay. That's the thing with college. If you like something, you'll learn it by yourself. Don't expect you can get it from the class because in the class we only go over the basics. Second is Second is not some rule, but it's personal experience. That is something I believe. In order to learn 80% of what you need, you only need 20% of the time. Okay, but probably you spend only, I don't know, 2 weeks. You can learn Calculus 1 to a pretty decent extent. The other 80% time you spend on a class is try to learn the 10% or 20% left. Sounds good? That's how we construct the whole thing in 100%. You will learn a lot of things which is not necessary. Okay? So if you want to get to know some field, don't be afraid and say, hey, who am I? I'm just a sophomore. What do I know? I know nothing. So I'm not ready to learn that. No, you're ready. Okay? Whatever you want to learn, you're ready already. Sounds good? Just go there, spend 2 weeks on that. You will learn something that other people will learn in a whole semester. Of course, you will miss the last 10% or 20%, but if it's not your major class, why do you care? Okay? So try to learn it by yourself. How much you can get from your college is purely up to you. It's not up to the professor. All right. 3.9 related rates. We don't have time to cover anything here except for the concept. So very easy example to start with. So you have a snowball. Does everybody know what a snowball is? Okay, the first time I taught like 3 times this class in Alabama, I have to play a video for 4 minutes, tell them what a snowball is. Wisconsin is awesome, okay. Then, leave it there. Again, in Alabama, this thing is gonna melt. Okay. Now you see something really interesting. The volume shrinks at a certain rate. Meanwhile, as the volume shrinks, the radius also shrinks. At the rate. We call it dr over dt or r prime, v prime. Your surface area also shrinks. Okay, a lot of things, your mass also shrinks. Sounds good? Okay, so one phenomenon corresponding to the changing rate of a lot of parameters. Now the question becomes, are these rates related? Or say, if I know the changing rate of the volume right now, can I also calculate from that the changing rate of the radius? Does it make sense here? Okay, you have 4 things changing right now. If you know one of them, can you know the other 3? Because they're related. Sounds good? That's the idea of related rates. You have 2 rates. They are related somehow. So if you know one rate, you can find the other. Okay, why is it useful? Think about GPS. Think about the GPS system. What do you know? Well, number 1, you know a car is moving on Earth. Number 2, you know a satellite is moving in the space. Still okay? On Earth, you're driving at a certain speed. That's rate 1. In the space, the satellite is moving at a speed. That's rate 2. And somehow, by sending signals back and forth, these 2 rates are related. So if the satellite knows how fast it is moving, it will be able to actually calculate how fast you're moving on Earth. That's the whole point of doing GPS system. Knowing one rate and calculate the other. Sounds good? Okay, so related rates is actually really, really useful everywhere, but we will talk about it starting from tomorrow. Okay, that's all for today.